Now, shaft subjected to bending only. Now, previously we have done a few examples on design of shaft that is based on a failure due to twisting or due to torsion only. Now we are looking at the design of shaft based on bending only. This time is based on bending only. Okay, so shaft subjected to bending moment only. Then we have to refer to the simple bending equation. Okay, the simple bending equation also will be split up into two different sections that is based on strength relationship and stiffness relationship. So based on strength relationship, we have M over I equals to sigma over Y. What is this M here? M is the maximum bending moment. Okay, maximum bending moment. Or let's say, for example, if I want to take let's say bending moment at a section. I want to design a shaft based on a bending moment at a particular section. Then my bending moment will have to be taken at that particular section alone. Okay, but that will be in your degree because degree most of the time we are looking at different or varying sections of shaft. So for diploma, we assume that the shaft is made up of uniform external diameter. Okay, uniform external diameter. And then I is the moment of inertia. It's no longer polar moment of inertia. It's the moment of inertia, which is pi d4 over 64 now, not 32. Okay, or pi d4 minus d4 over 64. It depends on whether it's hollow shaft or solid shaft. Now, sigma is the bending stress, and Y usually is the vertical distance that we measure from the neutral axis. What is neutral axis? Neutral axis is the axis which passes through the center of gravity of the shaft, the center of gravity of the particular section. So if let's say we measure the vertical distance from the CG or from the neutral axis to the outermost layer, that means you got top and bottom. So that will give you the measurement, or that will give you the value of bending stress if we know the magnitude of Y. That means if we know where the Y has to be taken, okay, the Y from the center of the shaft. Let's say, for example, it is a hollow shaft. Then when you refer to a hollow shaft, of course, you have internal diameter and external diameter. So then if I want to measure the stress based on the internal diameter, then my Y should be equals to small d over 2. If I want to measure the maximum bending stress, usually is the outside. Okay, the outermost layer, that means the external diameter divided by 2. External diameter divided by 2. Okay, so if I measure internal diameter over 2, then the bending stress that I get will be minimum. If I take the external diameter over 2, the bending stress will be maximum. Whereas this and I, therefore, should be considered as a constant. So M is the bending moment in Newton meter. Simple torsion equation is torque twisting moment, which is also Newton meter. Then the I is moment of inertia measured in meter to power of 4. It's about the x-axis and the y-axis. It is no longer twisting moment. If twisting moment, this is J. That is polar moment of inertia. That is also meter 4. That is for turning moment. Now this is for bending moment. Sigma is the bending stress due to bending moment. Okay, the bending stress. Earlier we have what we call shear stress for torsion, for twisting moment. Now this is for bending stress, for bending moment. Y is the vertical distance that we measure from the neutral axis. Now earlier we have torsion equation. This is R, the radius. So for bending moment, we use the symbol of Y. represents the vertical distance from the neutral axis. Indirectly means it means the radius, the radius. Okay, so based on this, we have the equation. By considering the m and the I are constants, then we can develop an equation saying that for maximum bending stress, we have to refer to the external diameter over 2. For the minimum bending stress, we have to refer to the internal diameter over 2. So for torsion, for twisting moment, this is tau over r. Tau max over r max. Tau mean over r mean. But this is bending stress. So it's sigma max over y max and sigma mean over y mean. Okay, and then for stiffness relationship, we have m over I equals to E over R. Okay, torsion equation, stiffness relationship, we have T over J equals to G theta over L. So this is bending, so it refers to Young's modulus E, and this R as the radius of curvature. So bending moment, I is the moment of inertia, E is the elastic modulus or the modulus of elasticity, usually given in gigapascal or giganewton per meter square. 1 giganewton per meter square is 1 gigapascal, or 1 Newton per meter square is 1 Pascal. Okay. R is the radius of curvature. So based on bending moment, if let's say based on bending moment, then we have to use this relationship. We cannot use the T over J tau over R. Okay, that is for twisting moment. Okay, this is for bending moment. Now, how bending moment occurs? It's just like a shaft. So let's say, for example, you have a shaft, okay, a straight horizontal shaft. Then you have gears on top. You have pulley on top. So the gears, the flywheel, the pulley that you place on top of the horizontal shaft actually exert a force, a transverse force. That is the weight of the object itself. It will be acting on the shaft. When this weight here, based on the flywheel, based on the gear, based on the pulley, acting on the shaft, what happens? It will cause bending to the shaft. Okay, bending of the shaft. Follow? So now, bending stress, we know that this is bending stress. Earlier we have shear stress. Now we have bending stress. Okay, if it is a solid shaft, the moment of inertia here, which is taken about x or y axis, should be pi d4 over 64. Okay, if it is a hollow shaft, remember this is 64, yeah, not 32, 64, yeah. Okay, so you have based on external and internal diameter. Now, this component here, the bending moment, okay, for the bending moment, also it has to depends on whether the shaft is cantilever, simply support, cantilever with point load or with UDL load. Okay, simply support with point load or UDL load. UDL load means uniformly distributed load. If you have done MOEM, Mechanics of Engineering Materials, you should know. Okay, if we were to measure the bending moment, okay, we have to look into the shaft or the beams, whether it's simply supported, whether it's cantilever, what are the various type of forces and where they are located in order to find out the maximum bending moment. So since this is maximum bending moment, therefore we have to know what is the maximum bending moment for all these different conditions. First is a cantilever shaft that is in a cantilever form. This is cantilever. This is a very good example of a cantilever shaft in a cantilever form. So now there is a point load. This is called a point load, okay, or a concentrated load W, or due to the weight of anything you put here. Let's say a flywheel. We know flywheel is very heavy. If you put at the end of this shaft here, it may cause the shaft to bend like that. Okay, so that is a point load here. That is the weight. So we know that based on cantilever, very easily we got to know that the maximum bending should occur here. Should occur here at the fixed end here. This is called the free end. This is called the fixed end. So the maximum bending moment would occur here. So how are we going to measure the maximum bending moment? So standard formula, a standard formula based on this limited criteria for a cantilever with a point load acting at the free end, you can straight away take the formula of maximum bending moment for this value here. Okay, for this value here, the maximum bending moment can be equal to the W here times the length L. So the W here should be in Newton. The length here should be in meter or mm, but usually we use meter. So this is the cross section of the shaft, which is a solid shaft. Okay, which is a solid shaft. Hold on, yeah. Okay, a solid cantilever shaft. So if it's, let's say, for example, okay, uniformly distributed load, let's say, for example, you're subjected to the self-weight, of the beam, or the self-weight of the shaft, because shafts are lengthy and solid or hollow. It is made up of usually mild steel, okay, so that they consider a certain amount of weight. So that type of weight we cannot consider as a point load. So we have to consider it as a weight that is uniformly distributed along its length. So therefore, to measure the maximum bending moment, of course, the maximum bending moment also will occur here. So it's taken as omega L squared over 2. This is the standard formula. That is a different. This is WL. This is omega L squared over 2. This W here is in Newton. This omega here, that is the uniformly distributed load, is Newton per meter. Newton per meter. This is Newton. Okay? So remember this, these are standard cases. If let's say, for example, when you're doing a design of shaft, you have standard cases like that. So you can straight away use this formula here to find out its maximum bending moment. Yeah. So now, other cases like, for example, simply supported shaft or beam. Okay, let's say with a point load acting at the center of the shaft, then the maximum bending will occur here. The maximum bending will occur here. So what is the maximum bending here? So this is bending moment diagram, yeah? This is bending moment diagram. So the maximum bending will occur at WL over 4. W is the weight or the load in Newton. L is the length of the shaft divided by 4. If it is only with one point load acting at the middle. Okay, so that is your neutral axis. Now, if let's say the point load is not acting at the center, it is acting at any point here with a distance of A from one end and distance of B from another end. So how to find the maximum bending moment? So use this formula here. W is in Newton, A is the length here. It can be shorter than B, it can be longer than B length also, okay? A can be shorter than B, A also can be longer than B. Both you can use this formula here to find out its maximum bending moment, because we are going to apply the maximum bending moment to design the shaft. Okay, so now if let's say, for example, it's not point load, what about the shaft self weight? That means the omega or the uniformly distributed load. Then the maximum bending that is taken will be based on omega L squared over 8. Again, it is different from the W, yeah? The W is in Newton, the omega here is in Newton per meter. So in this case, it's omega L squared over 8. It's not omega L squared over 2. That is for cantilever. This is for simply supported. Okay, that's all for this part. Hope you all understand.